Hi, I'm Jim Heffron. These are my lessons in calculus. Bit of a dark day today, so I look a little. The camera's having a little trouble picking me up. So we're really kind of getting into it here, and so we're starting to be able to find the rates of change of whole classes of functions. So today we're going to find the rates of change of polynomials and also the rates of change of exponential functions. Now the second one will really just kind of give you the formula. So I have a kind of an editorial comment I want to make about the distinction between explaining the formula and giving you the formula. So in my line of work, you sometimes hear people say, I had a terrible teacher in high school. This is what people say. I had a terrible teacher in high school say they never explained anything. They just gave us the formula. So I always nod to that. That doesn't sound right to me either. But by the same token, I also have sometimes people tell me, in this section in particular, why did we bother with all that stuff from the previous chapter? Why don't you just give us the formulas? So in that context, I think I'm going to do what I think is right. So I'm going to do my best to explain where the formulas come from. Prove is a funny word. I'm not so sure about prove, but to give a person a very strong sense of what this is about. In particular, in the second case, for exponential functions, I'm going to give some explanation rather than just simply give a formula. If you like to just get the formulas, then I guess you're in the wrong shop. You're going to have to go somewhere else. Okay, let's get started. So let's see here. I want to remind a person that we found the derivative of f of x equals x squared at x equals a. For the moment, I'm writing a distinct from x just simply because I'm trying to emphasize that there's an anchor point. That's all. Pretty soon we'll drop that pretense. So the derivative, you'll remember, is the notation is f prime. And we take the limit as h goes to 0 of the difference quotient, and it all looks pretty familiar. Expand this is the square of a plus h, and cancel the a squareds and factor out an h, and we find ourselves down here with 2a. And so if you tell me a equals 7 or a equals 9 or a equals minus 4 or a equals 0, then I can tell you what is the rate of change of this function at 7 or 9 or minus 4 or 0 just simply by doubling the 7 or doubling the 9 or doubling the minus 4 or doubling the 0. Okay, rate of change of the squaring function at the input minus 4, the rate of change is minus 8. Okay, so that's convenient. That's a convenient formula. We call the 2a the derivative of the x squared function. Cubes. So a person might need some reminding here about how you cube, and so I expanded it here. You would cube by first multiplying out two of the terms, squaring, and then finally multiplying in the third, and you get this pattern here. So just to have gone through the pattern, the a's go power 3, power 2, power 1, and no a at all. The h's go no h, 1h, 2h, 3 h's. And as for the numbers, the numbers 1, 3, 3, 1, they come from Pascal's triangle. I'll remind you what Pascal's triangle is about. It's been my experience that folks nod vigorously when once I go through what Pascal's triangle is. So Pascal's triangle is you write a 1 and then a 1, 1. And now I'm going to make the new numbers by adding the 2 above and below. So I'm going to write a 2 here. And this one here, the one on the left, there's nothing above. So I'm going to write a 1 because it's just the sum of this one here. This 2 is these pair. And over here, going to write a 1. I suppose you could imagine that there's a 0 here, and so it's the combination of the 1 and the 0, I suppose. But anyway, we've got 1, 1, 1, 1, 2, 1, and you follow the same pattern. You see the 1, 3, which is the 1 and the 2 combined, and then the 2 and the 1 combined to make a 3, and then 1. And now I'm just going to do another line or two. 1, 4, 6, the 2 3's together, 4, 1, and then 1, 5, 10, 10, 5, 1, and etc. Obviously, you could keep that pattern up as much as you like. And again, the name people give this is Pascal's triangle. I don't know what connection Pascal had with it, but anyway, Pascal's triangle, and we're going to see a couple of other instances of these 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1, etc. as we move through the next couple slides. Okay, but so anyway, that's the cube. And so when I take the derivative, it's exactly the same thing. Here's the limit of the difference quotient. When you expand the cube, you get that thing I felt compelled to remind a person about. But then the patterns that we've seen so far all fall in. You cancel the a cubes. You factor out an h. And when you can't go to cancel the h's, then the only thing that's left is the 3a squared, because this one's got an h, so its limit is 0. This one's got, in fact, 2 h's, so its limit is 0. And so the derivative at a is 3a squared. So we have a formula for the derivative of the cube, and it's convenient. And as an example, f prime, the derivative at 5 is 3 times 5 squared, 3 times 25, so 75. Okay, and it's perfectly clear what I'm going to do next. I'm going to look at x to the 4th. And so at that point, we'll start saying, so we're seeing a pattern. So here we go, x to the 4th. X to the 4th, I reminded a person what the expansion of x to the 4th is, and do you see the 1, 4, 6, 4, 1 from Pascal's triangle? And again, the same pattern with the terms. There's 4 a's, 3 a's, 2 a's, 1 a, and 0 a's. And then there's also 0 h's, 1 h, 2 h's, 3 h's, and 4 h's. So there's a distinct pattern to what happens when you expand these things. And in particular, I'll just point this one out right here, that that number right there, that 4, is the same as this 4 right here. Okay, anyway, let me go through there's the limit of the difference quotient, there's the expansion, it's getting to be kind of long. You cancel the a to the 4ths, and what's left is a bunch of terms, every single one of which has an h. And of course, we're keen on that because we're going to factor out the h's. Every single one of them has an h. This one here has one h. The others have more h's in them. And it will turn out that the one with one h is the one I'm most focused on. Anyway, next line there, I factor out the h's. I'm looking at, in the parentheses, 4a cubed and some terms that have more h's, because up in the prior line, they didn't have h to the 1. They had h to the 2, h to the 3, or h to the 4. So when you factored out an h, you were left with more h's behind, and you end up with 4a cubed plus some terms that involve h's. When you plug h equals 0 in, you're allowed to plug in because no longer is it a limit with a denominator, a fraction with a denominator limit of 0. So you're allowed to plug in h equals 0, and when you do, the only thing left standing is the 4a cubed, and so that's the answer, 4a cubed. F prime of a is 4a cubed. Okay, so what's the pattern? We've done a couple of them, and you know, when you look at them 1, 2, 3, you say to yourself, what's the pattern? So for x squared, the pattern, you get a derivative of 2x. For x cubed, the derivative is 3x squared. For x to the 4th, the derivative is 4x cubed. And so it's perfectly clear when you look at these columns what the pattern is. You take the number that is the power and you write it in front. And then for the new power, you write 1 minus. Sorry, the old power minus 1. Okay, so it was a 5, now it's a 4. It was a 6, now it's a 5. It was a 7, now it's a 6. Written as a formula, the derivative of x to the n is n times x to the n minus 1. Okay, people sometimes say the n comes down in front, however you want to remember it. And again, what's happening here, where's it coming from? Well, that's the next slide. But nonetheless, it's perfectly clear that there is a pattern, and we're going to follow that pattern. And if I had just given you that on the sort of first day of class, then that would be memorizing the formula without explaining it at all. So what's the reason for the pattern? That f prime of x is n times x to the n minus 1. And I'm going to focus on the x cubed place, because the x cubed example, because I couldn't fit the x to the 4th example on slide. So here we go with x cubed. That's the calculation that was a couple slides ago, no different. Calculation from a couple slides ago. And I want to talk about what's happening there. Why is it a 3x squared? So the derivative is determined by the term with a single h. That is to say, this will end up being the derivative because at the end, after I factor out h and put in h equals 0, what will be left standing is the 3x squared. So why does that term have a coefficient of 3? How come when you're looking at cubes, you end up with a coefficient of 3? How come these two things, there we go, how come these two things are the same? So I'm cubing a plus h. I put them in red, in blue, and in black, hoping that it would help a person find the parts. So here I multiplied out a times the blue and black terms, h times the blue and black terms. And then in the next step, of course, I'm going to multiply out the blues. So I end up with an AA and an AH, also an HA and an HH. And then it's not very exciting, but anyway, I'm going to multiply each of these red blues times a black. There we go. I multiplied all the red blues times a black. I couldn't fit it all in one line. Oops, I made a stray mark. There we go. So I have 1, 2, 3, 4. Oops, 1, 2, 3, 4, 5, 6, 7, 8 terms. Total of 8 terms. 2 to the 3 terms, and I'm interested in the ones that have a single h, the ones that have a single h. Well, if you're going to have a single h, then what must be left is you must have 2 a's. So if you have a single h, then you must have 2 of the other letter. That explains why it says x squared. And why are there 3 of them? So to be an a squared h term, there's 3 letters. There's a red letter, a blue letter, and a black letter. Among the 3 letters, there needs to be exactly 1 h. And so how could that possibly happen? Well, it could be that h comes first, or h comes second, or h comes third. So that's 3 things. First, second, third. Count them out on your fingers. You get 3 of them. So the coefficient of 2 a's and 1 h is 3. And of course, that reasoning extends to any integer power. It would extend to the 4th, to the 5th, to the 6th, to the 7th, etc. So there's a reason for the formula. The formula makes sense. You can see why the formula is true. It's not just a question of slavishly following it. So I end up with the derivative laws for polynomials, and a person should memorize these, although I have to say most folks find they don't really need to memorize them so much as they just kind of do a bunch of derivative problems and they come easy. So the derivative of a constant function is 0. The derivative of a power, this is the one that we just talked through. The derivative of f of x equals x to the k is f prime of x equals k times x to the k minus 1. That's the one we just talked through. The derivative of a constant multiple of a function is you bring out the constant. If you have a plus sign, you break along a plus sign, and if you have a minus sign, you break along a minus sign. These last 3 all follow from the rules for limits. It's this one, number 2, that we've added today to what we knew before. Okay. So again, that formula is very important, although I have to say, although a person is expected to memorize, you should memorize it, but really, you do a half dozen of them and now you know it. But that formula is very important, and it holds for a reason. Things in mathematics are true for a reason. I wrote the same rules only in the other notation, in the ddx notation, just to have them in 2 different places. And in particular, here's the one that we just spent some time talking about why it's true. Okay, but now this does it twice, so I don't want to do it a second time. So practice, how I like to work. I like to, when we have something, I like to say, okay, stop the video, take out a pencil, and try this problem. So stop the video, take out a pencil, and try taking the derivative of this polynomial, 5x minus 4x squared. So break it along the minus sign, bring out the 5, bring out the 4, take the derivative of x and the derivative of x squared. Okay, go ahead. Okay, and the answer is that when you break along the minus sign and you bring out the 5 and you go to take the derivative of x, while the derivative of x is derivative of x to the 1, so you get 1 times x to the 0, and then 1 times x to the 0 is 1 times 1, because x to the 0 is 1, so you just got 5. And likewise, you've broken along the minus sign, so now you're going to take the derivative of x squared. So you brought out the 4, you're going to take the derivative of x squared. You bring down the 2, 4 times 2 is 8, and you knock the 2 down by 1, 8 times x to the 1 power, and we traditionally don't bother to write the 1. Next one, please. You see that that says x squared over 4. Okay, give you a second, you pause the video and give it a try. Okay, great. So you break along the minus sign and the plus sign, so that we now have 3 different derivative problems. The first one is to take the derivative of x squared over 4. The second one is to take the derivative of 3x. And the third one is to take the derivative of 9. So just going from left to right, the derivative of x squared over 4 is 1/4 times the derivative of x squared, because you're bringing out the constant 1/4. The derivative of x squared is 2x. So derivative of 1/4 times 2x makes 1/2 x. Next, you take the derivative of 3x. I broke along the minus sign, so there's a minus sign there. Take the derivative of 3x. Derivative of 3x is 3 times 1x to the 0, so it's just 3. And then broke along the plus sign, the derivative of 9 is 0. Constant function doesn't change, so its rate of change is 0. Okay, next, please. This says hint there. Hint, use the fractional power. So do you remember that the square root of x is x to the 1/2 power? Try it with x to the 1/2 power. Okay, and the derivative of the 1/2 x to the minus 1/2. So I brought the 1/2 power out in front, and I knock the 1/2 down by 1. If you take 1/2 and knock it down by 1, you don't get 0 halves. You get minus a half. So this is the same thing as a 1/2 times. Remember that a negative power means on the bottom of the fraction. So 1/2 times x to the 1/2 power. And you can rewrite that as 1/2 times 1 over square root of x, if you like it. So you could rewrite that as 1 over 2 square roots of x. You might see any of those 3 versions all written in various problems that we do in the future. Okay. Next one. So it says x cubed times x squared minus 4, and you don't want to take that as the derivative of x cubed times the derivative of x squared minus 4. We don't yet know how to take the derivative of a product, and in particular, what I just said is not right. So you want to multiply through first. Multiply through the x. Take the x cubed and multiply through, and then take the derivative. Okay. Okay, when you multiply it through, you get x to the 5th minus 4x cubed, and starting to go a little faster now because I think this is not very hard once you've seen a couple. So derivative of x to the 5th is 5x to the 4th. I'm breaking along the minus sign so that now I'm taking the derivative of 4x cubed. Derivative of 4x cubed is multiply 4 times 3. You get 12, and knock the power down by 1, and you get x squared. Okay, so we already ran across the fact that we don't know how to take the derivative of a product of 2 functions. We can take the derivative of the addition of 2 functions, the sum of 2 functions. Same thing with subtraction, and we can take the derivative of what happens when you multiply by a constant. But we don't know how to multiply by a variable or, in general, any kind of function. So f of x times g of x, we don't know, and it's not the derivative of f times the derivative of g. Likewise, we don't know how to do quotients, and we don't know how to do compositions. They got to come eventually, but you can't do everything all at once. So we also don't know how to do exponential or logarithmic functions, or trig functions or inverse trig functions. We have to work all those through. That's chapter 3. We have to have something to do in chapter 3. I'll say that today, next, we're going to do exponential functions because we want to use them when we take the derivative of the product of 2 functions. So we need to use them for some of the exercises. But today, we're just simply going to talk about the formula rather than really make sense of the derivative. Okay, so we're taking the derivative of exponential functions, but again, just cautioning a person, I'm going to do some explaining about where it comes from, but it's not really a derivation, it's more hand-wavy. Okay, so I'm going to remind you how to how to draw an exponential function and talk about what its rate of change is. So I'm going to cover the rules for the derivatives of exponential functions, and the reason is that I want those, the author of the book, and me included, want those to do homework questions in the next couple sections. So rather than just produce the formula for exponential function, I'm going to do a certain amount of hand waving. Right? And the formula, the derivation of the formula will come later, but at the moment I'm just going to do some hand waving. So I drew a graph of 2 to the x and a graph of 3 to the x, and they look enough alike that a person thinks to themselves, okay, I can see there's a pattern here. They have this characteristic upward sweep as you move from left to right. I want to, if you'll indulge me, I want to do a numerical estimate for the derivative of 2 to the x. So I did the numerical estimate up here for a equals 2. And you might remember, I hope you remember numerical estimates from before. So 2 to the 2 is 4. There we go, there's the 4. And then I tried points nearby to 2. So I tried a point that is 1 away, and a point that's 0.01 away, and a point that's 0.001, and found the value of the function. Found the value of the function at each of those spots. And then I later on calculated delta y over delta x to get the secant lines. And likewise with negative delta x's. I calculated delta y over delta x to get the secant line. And it's perfectly clear here from the numerical that we are converging here on a 2.773-ish. Not a proof of any kind, but at least some kind of numerical evidence. Now I wanted to also do a equals 0, a equals 1, and a equals 3 to fit with my a equals 2, and I couldn't get it all on one slide. So this is 3 different tables. 3 different tables. I apologize, but my point here is the delta y over delta x's converge to a number. The delta y over delta x's converge, oops, sorry, wrong place, converge to a number. Converge to a number, and the delta y over delta x is converged to a number. So on the next slide, I'm presenting some numerical evidence, and it's on the basis of these 4 tables. Okay, so we have some numerical evidence for what the rate of change of the function y equals 2 to the x is. And on the previous slide, I had a 2.773 for a equals 2. And here, this summarizes the previous slide here for the other cases. There's the 2.773 a equals 2 case that I just talked about just a second ago, and the other cases are a equals 0. The delta y over delta x is tended to 693. A equals 1. The delta y over delta x is tended to this, and a equals 3. Did I just say a equals 1? The delta y over delta x is tended to 1.3865. A equals 3. The delta y over delta x is tended to 5.545. So at least glancing at that, a person might not see a pattern, but I'm going to do a small manipulation here. I'm going to take that rate of change number from all 4 of those columns and divide it by the value of the function. So if you take 0.693 and divide it by 1, you get 0.693. If you take 1.3865 and divide by 2, you get 0.693. If you take 2.773 and divide by 4, you get 0.693. And if you take 5.545 and divide by 8, you get 0.693. I mean, come on. So there's something there for sure. Okay, so the rate of change, this number here, this line here, the rate of change seems to be proportional to 2 to the alpha. That is to say, if there is some constant, namely 0.693, where if you take if you take 0.693 and multiply it by 2, you get this number. If you take 0.693 and multiply it by 4, you get this number. If you take 0.693 and multiply it by 8, you get this number. So there's a constant proportionality. The rate of change at a comma 2a, the rate of change at a comma 2a seems to be proportional to 2a. So the rate of change is proportional to the value with a constant of proportionality of 0.693. All right, so numerical evidence, not a proof of any kind, but nonetheless pretty compelling. Doing the same calculation, take out a calculator, do the same calculation with f3 of x equals 3 to the x, and the constant proportionality is 1.099. So 2 is a little below 1, constant proportionality. 3 is a little above 1, constant proportionality. So somewhere between the two, is someone whose constant proportionality is 1. That number is called Euler's number. E, it's usually written as with an E, 2.718282. It's actually an irrational number. It's somewhat like pi. There's some analogy with pi. Irrational number goes on and on forever without repeating, without terminating. So below, I roughed out the graph. I got my computer to start at 0, 1 and give it a slope of 1. So there's a slope of 1. And then a slope of 2 at height 2, slope of 3 at height 3, slope of 4 at height 4, slope of 5 at height 5, and a slope of slope of 2 at height 2, slope of 1 at height 1, slope of 1/2 at height 1/2, slope of 1/3 at height 1/3, that kind of stuff. And when you do that, when you rough out the tangents at the various heights, again, slope of 1 at height 1, slope of 2 at height 2, slope of 3 at height 3, slope of 1/2 at height 1/2. When you rough out the tangents, you get this characteristic upward sweep. And so this is a graph of 2.718282, etc. to the x. So it's an exponential function, and it has the property that its rate of change is the rate of change of f of x's rate of change is equal to the slope of 1 at height 1, slope of 2 at height 2, slope of 3 at height 3 is equal to the height. The rate of change equals the height. Okay, the rate of change equals the value. So the formula is that if you pick Euler's number, the rate of change is equal to the value. Their same formula. If you pick some other number, like 2 or 3, then the rate of change is proportional to the value, and the constant of proportionality is the natural logarithm. So 0.693 was the natural logarithm of 2, 1.099 is the natural logarithm of 3. But this is the formula that we're especially keen on. The rate of change is equal to the value of the function. Rate of change is equal to the height of the function. F prime of x equals f of x. Okay, so you know how I work. I like to, before we leave the slides, I like to have practiced one or two, so a person coming to the homework should at least feel like, okay, I got the first couple. All right, so I'm going to ask you to take the derivative of the exponential function where the base is not 2 or 3, but instead the base is 5. Okay, so I'm just simply applying this formula right here. And let's see. So the answer is it's 5 to the 5. That was the b to the x part. It's 5 to the 5, ln of 5. And I didn't bother to write out what ln of 5 is. I didn't bother to punch it out on my calculator. Okay, next, 3 to the t plus 2t cubed. So this is a combination of a polynomial type part that we already know how to do, and the new type, the 3 to the t. Okay? Okay, good. So you break that along the plus sign. You find yourself taking the derivative of 3 to the t. You use this formula for taking the derivative of 3 to the t. And also plus the derivative of 2t cubed. So there's the derivative of 3 to the t, and there's the derivative of 2t cubed. For the derivative of 2t cubed, it's 3 times t squared. And then don't forget the times 2. So 3 times 2 makes 6. Another one like that? Okay, good. So we got to break along the plus sign, and the derivative of e to the x and the derivative of 4. Derivative of 4 is the rate of change of a constant, so that's 0. And the derivative of e to the x is just e to the x. It's a little weird that the derivative of a function is the function itself, but that's the point of e to the x. Okay, another one. Really, the only difference here is that it's got a minus, so you take the derivative of x squared, you write down a minus sign, you take the derivative of 5e to the x. Okay? Okay, great. Okay, so next up we're going to be thinking about what is the derivative of a product of two functions, what is the derivative of a quotient of two functions, what's the derivative of a composition. Okay, very good. Okay, looking forward to that.